In this video, we shall look at a few review problems associated with magnetic force on a charge. First, a brief introduction. Assume that you have a charge whose strength is Q. Let's assume it's moving on an xy plane. So that is the y-axis and that is the x-axis. So the z-axis is going upward. Let's assume the object or the charge is moving with a velocity v on this xy plane. In the region in which the charge moves, there is a magnetic field heading, say, in that direction. The magnetic field would interact with this moving charge to create a magnetic force on it, and the direction of this magnetic force is like that. The direction of this magnetic force is perpendicular to the plane containing the velocity vector and the magnetic field vector. The formula to calculate this magnetic force that is acting on this charge due to this magnetic field B is given by the following equation, namely Q V cross B, where V is the velocity vector of this charge and B is the magnetic field vector in which the charge is moving. 2 points are to be noted here. The first point is, if the charge moves in a direction parallel to the magnetic field or anti-parallel to the magnetic field, then the magnetic force on that charge is 0. The reason is because when the motion is parallel to the magnetic field, alpha is 0. So that means the magnitude of that magnetic force, which is given by QVB sine alpha, would go to 0. The same thing happens when the motion of the charge is anti-parallel or opposite to that of the magnetic field. Sine 180 is also 0, so the magnetic force on that charge would vanish. Point number 2. Magnetic force is only non-zero if the charge is moving. That is to say, if you were to place a stationary charge in a region with magnetic field, that charge will not have any magnetic force exerted on it. So for F to be non-zero, the charge must be moving. Of course, when we are talking about force here, we are talking about magnetic force exerted by this magnetic field on that charge. Now let's do the problems. Problem 1. A proton moves perpendicular to a uniform magnetic field at a speed of 1 times 10 to the power 7 meter per second, and it experiences an acceleration of 2 times 10 to the power 13 meter per second squared in the plus x direction when its velocity is in the plus z direction. Determine the magnitude and the direction of the magnetic field. Since we are given the acceleration to be in the direction of positive x, that must also be the direction of the magnetic force according to F equals to ma. But in this case, the net force F is provided by the magnetic field. Let's call it F sub B. So we can write F sub B, which is ma, equals to Q V cross B. We know the acceleration is in a I hat direction because I hat is the unit vector along the positive x axis. We are told that the velocity is along the positive z direction. So it's along the direction that is defined by the unit vector k hat. So what should the direction of magnetic field be? Let's look at the axis. If this is the x-axis defined by unit vector I hat, that is the y-axis defined by the unit vector j hat, then the z-axis defined by the unit vector k hat would go in that direction. So the question is, what should you cross with k hat so that the outcome is along the positive I hat? The answer is pretty clear. It should be minus j hat. So when you cross your right hand fingers, or you curl your right hand fingers from k hat to minus j hat, your thumb will be pointing in an I hat direction, which is indeed the direction of the magnetic force, or the direction of the acceleration. So immediately you know the direction of the magnetic field is minus j hat, or along the negative y-axis direction. Now we can go ahead to determine the magnitude of the magnetic field. So the left-hand side of this equation is mass times the acceleration. The right-hand side is q v b. And the reason is because the direction between k hat and minus j hat, the angle between them is 90 degrees. So sine 90 is 1. So the right-hand side would simply become qvb. This is proton. So the mass of the proton is 1.67 times 10 to the power minus 27 kg. So if you put that in there, 1.67 times 10 to the power minus 27 kg. Acceleration is given by that number, 2 times 10 to the power 13 meter per second squared. The charge of the proton is 1.602 times 10 to the power minus 19 coulomb. The velocity or the speed of the proton here is 10 to the power 7 times b, and you can solve for the magnitude of the magnetic field. And once you solve it, you get the following number. The magnitude of it is 0.021 Tesla. So if you want to express this answer in vector form, this is how you do it. It's minus 0.021 j hat Tesla. And that solves the problem. Problem 2. An electron moves with a velocity of that. So this is a velocity vector for that electron in a region in which the magnetic field is given by that vector, the unit of which is Tesla. What is the magnitude of the magnetic force this charge experiences? So in this case, the magnetic force is given by the following expression: the charge, the cross product of the velocity vector and the magnetic field vector. Now this is an electron, so the charge is minus 1.602 times 10 to the power minus 19 coulomb. Let's write down the cross product in a determinant form. So I, j, k. So the velocity vector, the x component of the velocity vector is 2, the y component is minus 4, and the z component is 2. Now let's look at the second vector, which is the magnetic field vector in the cross product. The x component is 1, the y component is 2, the z component is minus 3. So now we need to do this cross product. So you can write down the charge of this electron. It's just a constant outside. Now let's do this cross product. First, we cross out the I hat in mutually perpendicular directions. So this times that is 12. 12 minus 4, that's 8. So 8I. Now let's cross out the j in two mutually perpendicular directions. So 2 times minus 3 is minus 6, minus 6 minus 2 is minus 8. So there will be a minus in front of j, which is part of that cross product equation. So that's minus 8 goes there. And finally, the k component. So we cross out the k in two directions. So this is 4, 4 minus 4. And that's going to give you 8. We note that this minus will kill that minus, and that's going to give you a positive 8j. Now we can compute the magnitude of this magnetic force. Let's just write the magnitude of that charge, 1.602 times 10 to the power minus 19. To determine the magnitude or the length of this three-dimensional vector, you take the square of the components and then sum them up. and take the square root. And the entire line will give you the following answer for the magnitude, namely 2.22 times 10 to the power minus 18 newtons, and that solves the problem. Problem 3. A cyclotron designed to accelerate protons has a magnetic field with magnitude 0.5 Tesla over a region of radius 1.5 meters. What are the cyclotron frequency and the maximum speed acquired by the protons? Let's assume you have a circular region of magnetic field. The magnetic field is going into the plane, like that. And you have a proton moving in this region of magnetic field with this velocity to the right at the bottom. We note that according to this cross product rule, which says the magnetic force on that proton is given by QV cross B. So at the very bottom, the magnetic field would exert a magnetic force in a direction that is upward. So it would slowly deflect the proton upward until it gets to the right-hand side. On the right-hand side, the velocity is going up, and the magnetic force it feels at that position due to the magnetic field would be leftward in direction. And that means the magnetic force will slowly deflect the proton to the left until it gets to the topmost position. At that point, the proton would be moving to the left. The magnetic force would be directing downward, and that would slowly deflect the proton downward like that until it gets to the leftmost position. When the proton is at the leftmost position, it would be moving downward, and it would experience a magnetic force to the right that would slowly deflect the proton until it gets to the bottommost position where it started. So you see, in this case, the proton traces out a circular trajectory with radius r, and r is given by that 1.5 meters. Because this is a circular motion, the centripetal force, which is given by mv squared over r, is provided by the magnetic force, and magnetic force is given by qvb. This v goes away. V over r is what we call the cyclotron frequency, omega. The right-hand side is q times b. So you can solve for omega, which is q times b over m. Q is the charge of the proton, 1.602 times 10 to the power minus 19 coulomb. B is the strength of the field, 0.5 Tesla. It's given right there. Mass of the proton is 1.67 times 10 to the power minus 27 kg. And that means your cyclotron frequency is 4.8 times 10 to the power 7 radian per second. So that is the answer for part A. Now let's do part B, the maximum speed acquired by the protons. That is the maximum value of V. That is given by the radius of the trajectory times the cyclotron frequency. The radius of the trajectory is 1.5 meters. Omega has been calculated in part A, 4.8 times 10 to the power 7 radian per second, and that's going to give you 7.2 times 10 to the power 7 meter per second. And that solves the problem. Thank you for watching.